Now let's apply the same ideas for a loop of wire that has a current in it, and the loop exists in the YZ plane, and the length here is A and the length here is B, and the current is going in this direction as shown. And the loop exists in a region where there's a magnetic field, a uniform magnetic field pointing in the J direction. So we want to calculate the torque on this loop for the specific case when the magnetic field is parallel to the loop, which is pointing in the J direction. Now let's calculate the torque first on the left side of the loop. So in principle, when you calculate the torque on the left side, you should cut up the side into small parts and then get the torque due to each part and add them up to get the total torque. But it really turns out that there's a very simple simplification that can be done. You can consider as if all the force is acting at the center of mass of that side, and you can just then take the vector that points from the origin to the center of mass as if all the force is applying at that point. So this is what we're going to do, and then the torque in this case is going to be the R2 vector crossed into F2. F2 is the total force on this left side, and the total force on the left side we obtained it before. We derived it before, so if you don't remember this, please go back to that video to see how we got this result. So the torque is R2 cross F2. So what's the magnitude of the torque first? It's R2, F2, sine of the angle between them, but the angle is 90 degrees. So that you get sine 90, which is 1. So you just get R2, F2. Okay, and R2 is just this length, and this length is just half this length, so it's B over 2. So R2 is just B over 2, and the force is IAB, and so then the torque, the magnitude of the torque is B over 2 IAB. So what about the direction of the torque? If you get R2 crossed into F2, it'll give you something in the k hat direction. So the direction of the torque is in the k hat direction. So if you want to write the torque as a vector, it has a magnitude B over 2 IAB, and it has a direction in the k hat direction. So that's the torque due to the left side. Okay, what about the torque on the right side? So again, the total force acting on the right side is minus IAB I hat, and we can assume that the torque is going to be obtained by getting the position vector from the origin to the center of mass of that side, as if all the force is acting at that point. So it's R4 crossed into F4. So first let's get the magnitude. Magnitude as before, it's R4, F4, sine of the angle between them. The angle between R4 and F4 is 90 degrees, so you get sine 90 is 1. So it's just R4, F4. Now this distance is again B over 2. B over 2 IAB. What about the direction? Well, if you get R4 crossed into F4, it'll give you also k hat. That means the direction of the torque is in the k hat direction. So the torque on side number 4 is in the k hat direction also, and it has exactly the same magnitude as the torque on the left side. So the total torque is the torque on both of those sides, on both of those sides. Add them and you get twice the value. Twice the value means the half is gone, so you get IAB times the magnetic field in the k hat direction. A times B is the area of the loop, so we can write the total torque as the current times the area of the loop times the magnetic field in the k hat direction. So the conclusion, this is the final conclusion, and you have a force on the left side, you have a force on the right side, and the total torque on the whole loop is just the magnetic field times the area, B times A is the area, and then times the current in the k hat direction. And as we said before, if you put your thumb in the direction of the torque vector, then the fingers will be pointing in the direction that the object wants to rotate. You can see that this force and this force are trying to rotate the loop this way. And so if you put your thumb in the direction of the torque vector, the fingers will tend to rotate in the direction of the rotation of the object.